Morning, all of you again. So I'm going to present research work which is done at IIT Jammu only. So the authors are Mr. Ummer Rashid, Dr. Mehran Manzoor Zargar, Dr. Archana Rajput, and myself, Dr. Kushmanda, Saurav. So the title of the paper is Experimental Realization of Single Layer Triple Band Microwave Network Cloak. So outline, this is the outline of the presentation. We will give a brief introduction of Cloak and then about the proposed Cloak design, simulation results, and conclusion, and finally references. So concept of cloaking is that if you want an object to be optically transparent, if you want an object to be electromagnetically transparent, so we can do it by just trying to ensure that there is no scattering from it. So like if there is an incident wave and there is a reflected wave and transmitted wave and scattered wave, it's the general case. Like when a wave is incident, some portion will be reflected, some will be scattered, and some will be transmitted. So this is the case, like the object is now is visible to electromagnetic wave. But now if you want the object to be invisible to electromagnetic wave, then we need to reduce the reflection and scattering. Okay, those need to be reduced. So when we are reducing the reflection and scattering, then we can say that the object is electromagnetically invisible. Okay, but it will be definitely a frequency selective thing. So the invisibility can be achieved at some band of frequency. So for some band of frequency, the object will not be detected by electromagnetic wave. So if we coat the object with a cloak layer. Okay. So what we are going to present? We are going to present a microwave network cloak. So we are going to wrap a perfect electric conductor cylinder or a copper cylinder conventionally with some set of antennas, which are patch antennas, which will be connected by help of transmission line. So this will ensure that there is it will enhance the transmission of the wave. Okay, compared to like if there is a copper cylinder, so what will happen? So copper cylinder will be reflecting and will be reflecting the wave. So we will get a lot of scattered wave, and the transmission is very poor on the other side. But if we coat the copper cylinder with a series of this conformal patch antenna, so then we can enhance the transmission. So to enhance the transmission, what we have to do? So copper cylinder, we have considered it's a cylindrical in shape. So whenever a wave is going to pass through it, so it will take some, there will be a phase delay of the, like if the wave is going to propagate around the circumference of the cylinder, so it will take some extra path will be taken by the wave. So what the concept is that this conformal patch antennas will be designed so that this extra path length is compensated. The patch antenna at like below its resonance frequency, the wave propagation is more than the speed of light. The concept is that, so once the wave is going to propagate through the conformal patch antenna, so it will compensate the extra path length will be compensated by the high wave velocity, and then we will get a good transmission once the structure like the wave is going to cross the cylindrical step geometry. So the problem we address in this design is that this is like a single layer structure, and it can hide a scatterer. Scatterer means the copper cylinder. Copper cylinder size of order 1.16 lambda. 0.16 lambda means that is the diameter of the copper cylinder, and lambda is calculated with respect to the lowest frequency. And thin cloak layer, so layer of that like conducting cylinder, we are wrapping with some layer. So the layer of the thickness of layer is 0.03 lambda. And we have done the experimental verification of biostatic scattering reduction to validate the concept. So this is like the mathematical expression of total scattering. This is sigma 3D is the total scattering cross sectional. This is for the volume, and this sigma 2D is for the surface area. So we are going to take the sigma 2D in our present study. Like volume, like we are taking the height of the cylinder to be very large, so it can be considered to be infinite for that operating frequency. And we are doing we are calculating the normalized total scattering cross section. That is the scattering cross section of cloaked object, which is normalized with respect to the scattering cross section of the uncloaked object. So uncloaked object is the conducting cylinder, and cloaked object is the conducting cylinder wrapped by these patches. So ideal of perfect cloak, the value of scattering cross section will be 0. That is, the scattering of the object is reduced to 0. That is the ideal case. But we will be comparing the scattering cross section with respect to a copper cylinder. So this is like the schematic of the cloak design, where like this is a unit cell, where it is a microstrip patch antenna, which is which will be interconnected using microstrip line. This is the like cross-sectional view. Like R1 is basically denoting the radius of the copper cylinder, and there is some air space. Air space is there, so that is R2 minus R1, and then after the air space, there is a dielectric. Dielectric is uses 0.25 mm thickness, FR4. So L is the length of the cloak in the vertical direction. So these are like 3 operating frequencies. So that this operating frequency, like originally, like the patch antenna, this, if this element is considered simulated as a through a single port as a patch antenna, so it will be providing resonance at 3 frequency. Okay. So corresponding to this frequency, we are going to get the operating frequency of cloak also. So like we are again, what we are doing, we are comparing the scattering cross section with respect to a copper cylinder. Copper cylinder is the perfect scatterer, so that is going to give the normalized scattering cross section of 1 in the entire frequency from entire frequency band. So once like this copper cylinder is coated by this this microstrip patch sort of structure, we are getting the scattering reduction at these 3 frequency, and the normalized scattering cross section reduction is 0.15, 0.37, and 0.11 at these 3 frequency. So the maximum reduction is maximum reduction like for 0.11 is like close to 90%, and minimum reduction of 63% are observed at 5.6 and 5 point and 3 point sorry, it should be 4.55 gigahertz. So this is like we are getting the scattering cross sectional reduction compared to a copper cylinder. So this is like summary of the like cloak design. So the mode of operation is TM to Z, and operating frequency 3.4, 4.55, 5.65. Total biostatic scattering cross section is 0.15, 0.37, and 0.11. And if we calculate the 50% bandwidth corresponding to 50% scattering cross section, it's like 3.8% in the lowest frequency, 1.5 in the middle frequency, and 9.4% in the uppermost frequency. So radius of conducting cylinder is 0.22 calculated at the lowest operating frequency, and 0.037 calculated at the highest frequency. And thickness of cloak layer is 0.03 at the lowest frequency and 0.06 at the highest frequency. So this is electric field distribution. First case is that when cloak and there is like conducting cylinder is not present, there is only like free space case. That is the ideal case. Okay. So ideal case like all the wave is basically transmitted because there is no structure. So this is the reference measurement. So like all the wave is transmitted. Now if we place a copper cylinder in the middle, so what happens due to scattering and reflection? So like this transmission is very poor. Okay. So now if we coat this copper cylinder with the cloak structure, so transmission relatively improve compared to the PEC case. And it's quite similar to the first case, but although it's not a perfect cloak, so we are not going to get the exact 100% transmission, but we are going to get a good transmission at the three frequency of interest like 3.4, 4.55 and 5.65 gigahertz. So this is the fabricated sample, and yeah, the measurement has been done using the free space technique, using vector network analyzer and pair of antennas. So the antennas like this distance is like they are kept in the this structure is kept in the far field of the antenna, and the measurement have been taken as S21 parameter through a vector network analyzer. So then again, like scattering cross section is calculated for first we have calculated for PC object with respect to PC object with respect to free space, that cloaked object with respect to free space, and then we are basically taking a ratio to get the total scattering, that normalized scattering cross section, and that this is the formula like for an object, if you want to calculate a scatter field, we have to calculate with respect to the free space. Now this is the measured result. So measured result, we are getting like a bistatic scattering reduction of 0.25 at 3.42, 0.4 at 4.49, and 0.22 of at 5.52 gigahertz. So this is the measured like scattering cross section reduction bandwidth corresponding to 50% scattering cross section. It's 4.11 in the lowest band, middle band it's 0.89, and upper band it is 14.4%. So I'm just concluding the work. Like we have presented a single layer conformal lightweight and low cost cloak, and we have compared the scattering cross section reduction with respect to the conducting cylinder, and there is a close agreement, not exact but close agreement with the simulated. Thank you.